Okay, Stefano, can you please introduce the session?
Thank you very much. So welcome everybody. Thank you for joining the third session on LISA instrumentation. This is a parallel session on day 4 of the symposium. Today we will hear from BISCHOF from Hannover on the much awaited first performance measurement of the Three-Backlink experiment. Then Mattia VILLANI from University Urbino in Italy will tell us about the relation between simulation of the test mass charging and the measurement on LISA Pathfinder. Then we will hear from Stephen Apple from the University of Florida about the stray electric field measurement, and we'll have a short break. And then we will we'll hear about simulating the micrometeoroid impact on LISA telescope, my God, and on the dimensional stability verification for the LISA telescope, a very important subject. And then from Ada UMINSKA, oh sorry, the first talk was from Corey Austin, and then Lorenzo SALA will tell us about the last paper from the LISA Pathfinder collaboration about everything we want to know on glitches. The question, as you may know by now, may be filed on the chat. You can even raise hand. However, it is appreciated if you anticipate your question on the chat anyway. And I think that we will see the question can be also asked on YouTube. And all that said, if I didn't forget anything, did I forget anything? No, then we can start with the first talk, which is by BISCHOF. Leah, can you try and share your view graph, and I'll give you a warning after 12 minutes, okay?
All right, thank you very much. And I hope you can all hear me and see my slides. Yeah, I'm Leah, and thanks for everyone for listening. I will talk about first measurements and the Three-Backlink experiment. And the work I'm presenting is a teamwork from the PRDS team at the AI in Hannover. So let's quickly start with what the backlink in LISA is. So in each spacecraft, we have our 2 optical benches, each in one of the movical optical subassemblies, the MOSAs. And these optical benches need to have an optical connection between them. And this is what we call the backlink, or the phase reference distribution system, in short PRDS. Since this backlink is part of the critical measurement parse for LISA, it cannot spoil the test mass or reference interferometer well, in any sense. So any noise that is added from this backlink has to be below the picometer per square root of Hertz requirement. And typically we're talking about the non-reciprocal effects. So since we send light through this backlink in both directions, the non-reciprocal phase, the difference between both directions, is what we call the non-reciprocity, and these effects have to be below the picometer per square root of Hertz requirement. Before I start with the Three-Backlink experiment, I would like to give you a short overview about the whole backlink understanding that we have to the present date. So the first investigations for a really LISA-like backlink experiment were done by Roland Flederman quite some years ago, and he used one fiber as a backlink and sent light through it in both directions. And he found that this setup is then limited by backscatter, because when you send light in the backlink through both directions, then any light that scatters at the fiber or at the TX fiber will just travel together with a nominal beam in the interferometer. And this backscatter is actually limiting the measurements. So in this experiment by Roland Flederman, this very first implementation with different kind of post-processings, this very high initial noise was reduced to the picometer level. There were further investigations on fiber parameters that are important for the backlink as a fiber by my colleague Max, and there's a very nice pre-recorded talk by him, which I can highly recommend to have a look at. So he investigated fibers, for example, for backscatter, and also for the coupling from temperature to the phase in these fibers. And his results, together with the results by Roland Flederman, were used in simulations, and they, well, to understand further what happened in this experiment by Roland Flederman. And they found that the phase noise due to the backscatter is driven by the temperature coupling. In this experiment, it was especially bad because the TX fibers were going through the laboratory where there's a very high thermal environment. So this backscatter problematic in a fiber backlink depends on thermal stability. This is something that we know. And accordingly, the baseline for LISA was chosen based on this knowledge. The design is actually similar to the experiment by Roland Flederman, but with additional improvements like attenuators in front of the TX and the backlink fiber. And the thermal requirement that was derived is a very important part of this baseline. All right, so this was just a rough overview about this understanding that we have. And in parallel, there were also investigations on finding a backlink that has by design less backscatter. And this led to the design of the three-backlink experiment. And this is an experiment consisting of 2 optical benches, so they can actually be rotated so that we get a LISA-like setup. And they are connected with the 3 different backlink implementation. And the whole design is optimized in backscatter and stray light because we already know from the previous experiment that this is a problem. So one backlink that's implemented here is a direct fiber backlink, and this is the one that is really similar to the one from Roland Flederman and thus also similar to the LISA baseline. Although we have here additional Faraday isolators, and they reduce the backscatter from the TX fiber so that we can actually investigate the backscatter coming from the backlink fiber. A second implementation of a backlink that we have is a free-beam backlink, where we removed the fiber and replaced it with 2 steerable mirrors with a DWS-based control loop. And here, because we have no fiber, we remove the fiber backscatter in this backlink option. And this was implemented in the three-backlink experiment together with Daniel, and he has a very nice poster presentation on how we did this and all the details about that. The second implementation is the frequency-separated fiber backlink, where we use an additional local oscillator to send through the backlink so that we have the backscatter light or the backscatter interference at a different frequency. The optical bench construction for the backlink was done in Hannover, and this is was a very challenging construction because we have a lot of interferometers and a lot of requirements for each component that we had to place. And my colleague Zhang Ji has a very nice poster presentation on that, which summarizes how we did that. So as I said, we want to measure the non-reciprocity in this experiment, and therefore we overlap the local beam with the backlink beam on both sides and combine the measurements on both sides. And what we get then is a noise term from the fibers and from the lasers in the TX and the TX dot beam. And then we have any kind of physical non-reciprocal effect that happens inside the fiber. We have the phase noise that comes from backscatter, which also has acts as a non-reciprocal effect. And then, of course, we have all kind of readout noise in an experiment. And all of this together is what we measure in our non-reciprocity. So this is all in one term. So this measurement is actually limited by this noise term. And normally in an experiment, you wouldn't use just a reference interferometer to subtract this noise term, but we don't have this here, but we have three backlinks, and they can act as a reference for each other. And therefore, we always combine them pairwise so that we can really measure what we want, so this non-reciprocal term. All right, so this very excitingly is our very first measurement with the 3-backlink experiment with all the 3 backlinks. So you see 3 lines, one for each backlink combination. And you can already see we are way above the 1 picometer requirement, and we are limited here by all kind of readout noise. We have a white noise level at 10 to the minus 4 radian per square root of hertz, and then this increase in the lower frequencies. And in the high frequencies, we were actually limited by a problem inside our phase meter. So we found that the performance was depending on which beat note frequency we are using. So just a phase meter internal problem. And by just choosing a different beat note frequency, we were able to reduce the noise for the direct fiber backlink and the free-beam backlink below the picometer requirement. The third backlink needs 4 different beat note frequency. Therefore, this is a bit more complicated, but this is not a problem from the backlink, but just from our readouts. So this is something we are working on. Then in the center frequencies, we have this high noise floor due to air fluctuations. So when we evacuate our vacuum chamber, this goes down and we see quite a different kind of noise shape here. And very prominent is the shoulder at 0.14 hertz. And we are very certain that this is laser frequency noise coupling in our measurements. So we can measure the laser frequency noise coupling in each backlink combination. And these are the graphs shown here. And we see the same prominent noise shoulder that we see below here in the non-reciprocities. Very interestingly, we only see it really in the combination that use the direct fiber backlink. So we think that because this is a backlink implementation with a lot of backscatter, that here the coupling works via backscatter. So laser frequency noise couples into a phase measurement with a path length difference here between the backscattered beam and the nominal beam it's interfering with. And this phase of the spurious signal then couples into a phase error on the left and on the right bench. And their difference is what's coupling into the non-reciprocity. And this is what we think we are seeing here. So this looks now like a problem. However, our laser frequency noise at the moment is much higher than we wanted to have in our experiment. So we use 4 lasers. They are stabilized on a reference laser, and they are this is stabilized on an iodine cell. And this stabilization has a problem at the moment, and therefore our laser frequency noise coupling is currently high as this, but with a running stabilization, it should be at least as low as this. And therefore, this is again just a problem in the laboratory that we are working on, because if we can have the stabilization running properly, well, this goes down much. And then also this coupling in the non-reciprocity will be below the picometer requirement. Another reason why we think this is actually due to backscatter is because we can add balance detection to our measurement. And then we see that this noise here is removed or reduced. However, it's just a very little reduction with balance detection. Normally, you would expect that it goes much lower, and therefore we are sure that there's a different noise source underneath that is currently limiting. And there's the cross-coupling issues that we also have in our phase meter, which have a similar shape. And also we see that the noise level here in the center frequencies really depend on our quality of the laser frequency logs. So again, this is some kind of readout problem that we are working on to reduce this noise floor. In the lower frequencies, we think that we are limited by temperature, which, well, as so often in low frequencies, and we can really see that our laboratory temperature couples in our phase measurements. And this is especially bad as soon as we activate our vacuum pumps, because somehow this additional heat load in the laboratory starts oscillations in our air conditioning, which is very unfortunate. So you see that here, a normal lab condition, and then with vacuum pumps running, you see this strong oscillation, which also couple into the sensors inside the vacuum chamber. And when we look at the non-reciprocity, we see here this bump at 2 × 10⁻⁴ Hertz, and here a plot of the temperature sensor measurements. They are basically at the same frequency, so we're very sure that there is some coupling happening. Again, it's mainly happening in the direct fiber backlinks. We believe it's somehow caused or coupling via backscatter, but we need some further modeling to really make sure that we understand the process. We also see here a temperature measurement for a sensor without the pumps running, so at a much lower level. And therefore, we are convinced that as soon as we, for example, use a house vacuum instead of the turbo pumps, we can also reduce the noise in the non-reciprocity. However, this measurement, I mean, you see we are really way above the requirement here, but it's very interesting because this high noise level allows us to probe on our understanding of the temperature to phase coupling in a backlink. And when we change the laboratory environment by using the pumps differently, changing the heat load, we will be able to have these measurements at different kind of temperature environments, and then we can really study our model on how this temperature to phase coupling in a backlink works. So, I mean, this is kind of a problem, but it's also kind of a nice opportunity. All right, so I showed you how we started with a measurement with a lot of noise, and showed you a little bit on what we did.
3 minutes to go.
All right, thank you very much. Yes. We reduced the noise in the high and in the center frequencies. And what you see here is our measurements, like our best measurements without any post-processing compared to the measurement by Roland Flederman. And you see that the goal of this backlink experiment to reduce the backscatter by design was already successful in these frequency ranges. We are quite sure that what we are seeing is some kind of readout and laboratory problem noise, and that's things that we are working on. For now, we can already say that the lines that I'm showing here are the upper limit for a backlink performance for a backlink that is operated under a temperature stability of 10⁻⁵ Kelvin per square root of Hertz. So the Three-Backlink experiment, the goal is to bring the noise floor to the 1 picometer per square root of hertz requirement. And then we can really investigate the backlinks for their performances. We have a lot of details like the rotation. We have 2 benches. We have 3 different backlinks, which allow us to disentangle the noise sources. And we have many possibilities for future measurements in order to study the backlinks and all kinds of parameters. One thing that we can do is to enhance the temperature environment to study our model from temperature to phase coupling. Except for this very high temperature stability of our backlink fiber, which is inside the vacuum chamber, the rest of the design and the components of the Three-Backlink experiment are a worst case study for LISA. So therefore, this is very helpful. Currently, we have an understanding of our laboratory noise, and we are working on improving that. So to summarize, I gave you first an overview about our understanding and the investigations that have been done and are still ongoing on really understanding how a backlink in LISA works. And this gives us confidence in the LISA baseline that was derived from these investigations. I also introduced to you the Three-Backlink experiment and showed you our first measurements and gave you the first understanding of our noise floor and how we plan to improve this noise floor. And as I just also introduced, as soon as the noise floor is low enough, we will be really able to probe all 3 backlink implementations for their non-reciprocal behavior. And yeah, thank you very much.
Thank you, Leah. Very interesting and very sharp on time. So question. I have a question from Dave Robertson. I missed why having the pump on increases the temperature noise.
It's a problem in our air conditioning. So somehow the heat load in the lab is higher, and it's not supposed to do that. It's yeah, it's a problem in the air conditioning.
Then I have
it's going to be fixed.
I have a question from Harry. Harry, why don't you ask the question directly?
Sure. Hang on.
It's a long one to read.
It was a question, if you can hear me, about how you are certain that the coupling of the low frequency room temperature fluctuations is directly acting or directly coupled via its action on the fiber rather than on some other aspect of the overall rather complicated setup.
So I mean, this is why I also said we need some more modeling to really be sure on how the coupling works. So I mean, there are even different points in the fibers where it can couple. So it can couple in the feed-through fibers. We definitely see that. And then it's a question of how good the common mode subtraction is, if that really is removed in the combination, because it should cancel in the non-reciprocity. And then there is the effect that it couples in the backlink fiber itself. And then, yeah, as you said, there are also other points where it can couple, but we think that the current model that we have is, yeah, it explains this, but it's not finalized. So this is why I didn't show this in more detail here, because I didn't want to show such a preliminary modeling. Hope that
thank you.
It'll
be good once you are able to not have the vacuum pump on, so that we see that there isn't any other layer of noise below what you see. That would be very comforting.
Absolutely. That's
thank you.
One of the next steps.
Thank you. Any other question? I have one question. Maybe I'm confused. I didn't get something. But by comparing the 3 link, aren't you always limited by the worst one?
Yes, that's absolutely true.
So if the LISA link is the best one, we could never know. We could, from your experiment, we wouldn't know.
Yeah, I mean, if the other ones perform bad, of course, but I mean, all of them were chosen in a way that they are expected to perform well enough. And so far, we didn't found any reason why one of the others would be worse than the LISA-like one. So, but it's true. Yeah, we can always only say it's a limit.
Then I have a question from Antoine Petitot. Antoine, please ask your question.
Yes, maybe I misunderstood something. A very nice talk. Thank you very much. But maybe I misunderstood something. Did you say that there is a link or a link between the noise and the bit note frequency, or it was something that you mentioned in one of your first slides? And you know that in LISA, the bit note frequency will evolve with time. So are we expecting that the backlink noise will vary with time because of this variation of the bit note frequency, or it's something that we can remove and it was just in your experiment?
No, we are very sure that this is just a problem inside our phase meter actually, so it's not connected to the backlink.
Okay. So
but
we are not
just,
expecting this for LISA.
No.
Good.
But
Thank you.
I mean, good point. I can understand why
Cross
this was.
finger.
I mean, yeah, from my view, of course.
Okay. Thank you.
Thank you. Other questions for Leah and this nice work? No. If not, well, thank you again, Leah. Thank you very much for this nice talk. And now we move to Mattia Villani, which is going to talk us about the bridging the gap between the pre-launch simulation and the measurement on board LISA Pathfinder, right?
Yes,
Thank
exactly.
you, Mattia. I'll give you a warning at 3 minutes before the end of your talk.
Okay. Good morning, everybody. I'm talking about the new simulation we carried out in Urbino University with our new Monte Carlo toolkit in order to simulate the test mass charging for LISA Pathfinder and compare these results with the measurements carried out on board the LISA. LISA Pathfinder was an ESA mission, a demonstrator satellite for the technology that we place on board LISA. It was launched on December 2015. It reached the L1 at the end of January 2016 and it operated until July 2017. The main aim of this mission was to study the noise budget of the instrument that will be placed on board LISA. And among these noises, there is the test mass charging due to the galactic cosmic rays and solar energetic particles. When talking about charging, there are two notions that are important. One is that of net charge, which is the algebraic sum of the charge deposited on the test masses. Here is the formula where J is the charge deposited and lambda J is the rate of the deposition. Then there is the effective charge, which is the sum of the square of the deposited charge. So there is a J square in the formula. LISA Pathfinder flew on the declining phase of the solar cycle 24. Here is the beginning and the mission, here is the end. The modulation of the galactic cosmic rays are reported here in this plot. At the beginning, it was this continuous curve for proton and helium. At the end of the mission, it was the dashed curve. And when the measurements were carried out, or test mass charging were carried out, it was this dotted curve. LISA will fly in the ascending phase of the solar cycle 26 with a similar solar modulation of the LISA Pathfinder. In our simulation, we did not consider particles with energy below 100 MeV because they give no charging to the test masses. For more information on the SEP and the galactic cosmic rays, it's a recorded talk by Katia Gremani. The pre-launch simulations carried out in 2015 gave this result. So the net charge was constrained between 14 and 32 charges per second, where the effective charging was confined between 170 and 300 charges per second. On April 2016, when the measures were carried out, they found that the test mass net charging was 23 charges per second. So it was well constrained by the simulations. While the effective charging was wrong, resulted underestimated by a factor 3-4, even including a contribution from other particles, which is about 15%. This is due to the fact that simulations were carried out with FLUCA and GEM4. This toolkit have a low energy cutoff for secondary particle propagation, and this is done to reduce the computation time. FLUCA has a cutoff at 1 keV for all secondaries, and GEM4 in 2015 it had a cutoff at 250 electron volt. Now with the new option 4, the limit is set to 100 electron volts. Among these low energy particles, there are low energy electrons, which were neglected in these early day simulations. But the point is that LISA Pathfinder and LISA will be very sensitive experiments. So low energy electrons cannot be neglected. In this context, the European Space Agency found it necessary to call an ITT with the aim to build a toolkit for the simulations, for the simulation of test mass charging, which included low energy electrons. We as Urbino University are participating to this ITT with the Trento University and OHB Italy. So in order to include all the low energy electrons, we had to carried out a survey on low energy electromagnetic physics. And we found that the most important processes are low energy ionization and kinetic emission, which is the production of electrons by a surface bombarded by charged particles. We also considered transition radiation and Bremsstrahlung, but we found that their contribution is negligible. Moreover, one has to consider the fact that at low energy, electrons behave like waves. So quantum processes must also be considered, and these processes are electron diffraction and quantum backscattering. All these previous processes were included in the new Monte Carlo program LEI, which was developed at the Urbino University. LEI is thought to work alongside with LUCA. LUCA propagates all primaries and secondary particles in the LISA Pathfinder satellite geometry up to the last 150 nanometer layer of gold coating of the electrodes and test masses. All these charged particles are propagated by LEI in this 150 nanometer layer, producing and propagating low energy secondary electrons in the range from 10 electron volts, 1 keV. Why 150 nanometer? This was chosen as a compromise because in our simulation we need to include all the low energy electrons, but these low energy electrons are millions. So we need to keep the CPU time under control. And this means that we had to reduce the thickness of the layer, and we found that 150 nanometer was a good compromise. The full geometry of LISA Pathfinder was implemented in LUCA with the program FLARE. Here is the CAD of the geometry. On the right, there is a zoom on the central region, which is the LISA technology package. Each of the two columns are the vacuum enclosure. The pink cube are the electrode housing. The blue part are the electrodes. The yellow is the test mass, and this is the optical bench. During the LISA Pathfinder mission, no SEP event with a flux above the background of galactic cosmic rays was detected. So in order to test the effect of SEP on LISA, we had to consider 3 historical SEPs. We chose one from the 1956, which is a very strong event measured on the ground with a neutron monitor, and 2 from 2006 measured in space by Pamela, which are weaker. Here on the left, we see the flux of these SEPs compared with that of protons and helium from galactic cosmic rays. This is the flux at the onset of the SEP for 1956, and we see that it is already 3-4 orders of magnitude larger than those of galactic cosmic rays. But the peak reached a peak of about 7 orders of magnitude larger of the galactic cosmic rays. This is the weaker event from 13 December of 2006, which reached a flux of about 4 orders of magnitude larger than those of galactic cosmic rays. This is the weaker event we considered, which is about 2 orders of magnitude larger than the galactic cosmic rays. Here on the right, we see our result for the simulations. We see that apart from the very weak event, which gives a charging comparable to that of galactic cosmic rays, and the other 2 SEP events give a charging of the order of thousands, or 1,000 charges per second, and the peak of the large event gives a charging of 130 million charges per second. Then we simulated the solar maximum and solar minimum, considering protons, helium-3, helium-4, nitrogen, carbon, oxygen, iron, and electrons. We see that the largest, in the net charge, we see that the largest contribute is from protons, then follows those from helium, and a large negative contribution from electron, which essentially erases that of helium. So in the end, the charging was about that of protons. Similarly, for the effective charging, we see that the protons give again the largest contribution, and that in this case, nuclei give a contribution non-negligible, of the order of 20% of the total. And in the end, we found that at solar minimum, the effective charging was 1530. Similar things can be said about the solar maximum, where the total net charge was 4.6 charges per second, and the effective charging 620 charges per second. Then we carried out a simulation for April 2016, when the measurement were carried out on board LISA. We considered protons, helium, and electrons. We see that the net charge resulted 22 charges per second, very close to the 23-24 charges per second measured on board LISA Pathfinder. And the effective charge resulted in 933.34, which is very close to the 1,1300 measured on board LISA Pathfinder. Based on solar max and solar minimum simulation I showed in the slide before, one should add to the effective charging a contribution of about 15-20%, bringing our result even closer to the actual measurement. So for my conclusion, that the Monte Carlo toolkit GM4 and Fluke have a low energy cutoff to reduce the computation time, and therefore, as a result, neglect low energy electrons. This resulted in an underestimation of the effective charging in the early day simulations. With our new Monte Carlo toolkit LEI, which allows for the production and propagation of low energy electrons down to 10 electron volts, we have filled the gap between the measurements and the effective charging, the estimated effective charging. So that was it. Thank you for your attention.
Thank you very much, Mattia. This was shorter than the time allowed, but very, very interesting. So, question for Mattia. While we wait the people to come up, I have a question, but now I'm confused, because I thought that the mismatch between the old simulation and what we saw in LISA Pathfinder was almost a factor 2, but we are saying that the electrons is something like, what is this, roughly 20% is, the electrons are completely neglecting the electrons made us make a mistake of 20%. And the rest is coming from helium. Wasn't helium included in the old simulation?
This is the old simulation. You see that the old simulation gave effective charging for 170 for the solar minimum, and 256 for, no, the end, contrary. 170 for the solar maximum and 300 for the solar minimum.
And Pathfinder was somewhere in between?
LISA Pathfinder was...
No, that's what we found, but the original prediction for April 2016 would have been a number in between P min and P max, right?
Should have been, yes. Should have been a number here in between, yes. But it was 1,000.
So this is a pretty significant underestimate. This is not completely explained by electrons, right?
No, why? With our simulation, you see that this is 933, and the simulation is
you're now fitting the observation, but the protons are more than we were expecting. From I see Tim Sumner is making a comment. Tim, do you want to comment?
Yes, you might as well finish the point you're already discussing first, though.
Yeah, no. It looks to me that the simulation now increase also the number of protons, right? They give a larger number of protons, a larger number of helium, or maybe I'm mistaken.
Well, if I can add something, because at that time Mattia was not here, so he was not here, so he didn't follow the details of these early days simulations. Of course, when we have carried out these first simulations, we didn't know which kind of galactic cosmic rays we were going to face in the spring 2016. So we made some predictions for the first part of the mission, the very first part of the mission, like the end of 2015, minimum, maximum predictions for that period. And of course, we now know that exactly what the flux was, because we have the data from AMS-02.
Okay. Tim, do you want to complete your comment?
Yes, okay. I'd first like to correct something that was said earlier on, that the low energy electrons were neglected in the original study. In fact, they weren't. There was an extensive discussion of them in the Araujo paper of 2005. And because of that, there were experiments done on LISA Pathfinder that explicitly looked for these low energy electrons by altering the bias on the test mass, because you would expect to see a dependence of the charging rate on the bias of any bias on the test mass. And one was a dependency was seen, but I believe it not be compatible with such a large noise rate, additional noise rate from the electrons. So I wonder whether you've looked at that additional constraint from the bias versus charging rate data from LISA Pathfinder.
So we did this extensive study on the processes that produce low energy electrons. And we found that these low energy ionization and kinetic emission were the most important.
So the question is, would the bias be relevant here? On any voltage bias on the test mass will be of big relevance?
Well, I come again because, again, I'm not sure if Mattia knows this. We have discussed this a lot with Valerio about the possibility to make basically negligible, if not zero, the charging. I'm not sure if this is the question. The charging on board. Is this the question? So with proper, voltage.
Yes, if I could explain a bit further, the kinetic emission electrons are low energy. They're with a work function of about 4.5 electron volts on the surfaces. All the electrons will be sort of around that energy, even lower. So when you start to bias the test mass up to a volt, you will alter you'll alter the transfer of electrons in both directions, either from the housing to the test mass or from the test mass to the housing. And that will give you a measured change in the charging rate as a function of the bias on the test mass. We're just finishing the paper on that for those data to be published. And that dependency on the voltage actually puts a constraint on how many secondary electrons can be present. And I think our conclusion is that you can't get up to the noise level that you need because of that constraint. So that constraint turns out to be critical to the discussion, I think.
Okay, sure.
Thank you, Tim. Thank you, everybody. I think this is becoming very.
This is not just a matter of simulation.
Any other question? Thank you, Katia. Any other question for Mattia? If not, let's thank Mattia again. This was a great talk. Thank you very much. Okay, and now the next one is from Stephen Apple from University of Florida, Gainesville, on the measurement of stray electric field via test mass charge modulation. Let's go. Thank you. And I'll give you a call 3 minutes before the end, okay?
Okay, great, thanks. Yeah, thank you for the introduction there. Can everyone see my screen okay?
Yes, perfect.
Okay, great. Yeah, thanks for coming, everyone. Today I'll just be talking about some of the work we've done at the University of Florida about demonstrating the measurement of stray electric fields via test mass charge modulation. So I think all of us are probably pretty familiar with the GRS at this point, but just as a quick overview, the LISA Gravitational Reference Sensor, GRS, provides a reference for the local inertial frame. You can see a picture of the Pathfinder GRS on the right here, and it consists of its free-floating test mass, its housing, and its actuation and sensing components, along with its associated electronics. And it also includes UV light injectors for a contact-free method of test mass charge management, which you can see kind of on the corners here, these light injectors. So yeah, overall, the GRS, along with LISA's drag-free control system, will help provide an ultra-quiet environment for the test mass, such that it's following a purely geodesic orbit and free-floating. So today I'll be talking about one source of noise on a LISA GRS, which is stray electric fields in the sensor. And stray electric fields can couple with an electric charge on the test mass and create a force that perturbs the test mass from its purely geodesic orbit. So the test mass and electrode housing surfaces have patch effects, which are caused by spatial variation in the electrostatic potential across the surfaces due to contamination of the gold surfaces. And these patch effects, combined with the voltage offsets in the electronics connected to the sensor's electrodes, can cause these stray electric fields. So very important to have a means of measuring and compensating for these stray electric fields in the sensor. And these stray electric fields are typically modeled as this delta X term here. And this term is basically the equivalent potential that you would have to apply to a single X electrode to produce the same force on the test mass as the stray electric field. So with LISA, the delta X must be measured with a calibration procedure where you essentially measure the force response in the sensitive degree of freedom for a given stimulus in the test mass charge. And once the delta X is measured, DC biases can be applied to electrodes in the sensitive degree of freedom to compensate for that delta X. And one method of measuring delta X that's been demonstrated both on the University of Trento torsion pendulum and on LISA Pathfinder was a DC method in which UV light was shined at the test mass or electrode housing surfaces to produce step changes in the test mass charge and measure the resulting force on the test mass. And with this technique that I'll be describing today, the test mass charge is modulated by shining pulsed UV light that's synchronized with an oscillating potential induced on the test mass with surrounding electrodes. And that's kind of illustrated in this cartoon here on the right, where the black curve is that oscillating potential induced on the test mass, and the purple square wave is the pulsed UV light that's synchronized with that oscillating potential. And some of the advantages of this charge modulation technique are that it's faster, more easily automated. The sensitivity can be optimized by choosing a modulation frequency where the sensor is more sensitive. And it also allows for the possibility of measuring delta X on multiple test masses simultaneously by choosing different modulation frequencies. All right, so we've demonstrated this method of measuring delta X on our torsion pendulum facility at the University of Florida. And you can see a picture of our facility here. The pendulum kind of lives in this thermal enclosure. And if you were to look inside the thermal enclosure, you would see our vacuum chamber. And inside the vacuum chamber, we have our torsion pendulum. So this picture is showing a CAD rendering of the pendulum inside the chamber. The pendulum consists of this crossbar assembly suspended by this 1 meter long, 50 micrometer in diameter tungsten fiber. And in this picture here, you can see our unsuspended crossbar a little bit better. So the crossbar includes 4 hollow LISA test mass mockups. at each of its ends. You can see two of them here, and the other two are inside their electrode housings. And the low thermal noise of the fiber, along with the light-weighted test masses, make it so that the pendulum is extremely sensitive to forces acting on the test masses. And this essentially gives us a near free fall condition in 1 degree of freedom. So the two test masses that are enclosed in these electrode housings are our gravitational reference sensors. We have a simplified sensor, and then we have a LISA-like sensor, which was the design was based off the LISA Pathfinder GRS. So it includes 18 electrodes for 6 degrees of freedom in actuation and sensing. And it includes 3 UV light injectors for UV LED-based charge management. So with the pendulum, we have 2 methods of measuring the position of our test masses. One is a capacitive readout scheme, which is similar to the LISA Pathfinder capacitive readout scheme. So with this method, the GRS measures the position of the test masses by measuring the position-dependent capacitance of a set of electrodes toward the test mass. And this is done by polarizing the test mass with a 100 kilohertz injection signal sent to electrodes in the GRS. And then these electrodes are, and then we read out the voltage from a pair of sensing electrodes connected to our readout electronics. And this voltage that we read out from these sensing electrodes is proportional to the test mass displacement. So in addition to the capacitive readout, we also have laser interferometer readout. Our interferometer is a polarization multiplex Mach-Zehnder interferometer, and this provides differential position readout of our test masses. And for the experiments that I'll be talking about today, we use the laser interferometer data and our LISA-like GRS. Okay, so moving along. So for these experiments, we used a prototype UV light unit provided by the UF Charge Management System Group. And this unit allowed us to generate UV light pulses synchronized with the sensor's 100 kilohertz capacitive sensing bias. And then we were able to linearly vary the phase of the pulsed UV light with respect to that 100 kilohertz signal to modulate the charge of the test mass at 1 millihertz. So this image on the right here is showing kind of the setup for the experiment. So this is our sensor. You can see in this experiment, we have one UV light injector, which this UV light injector 1 here, which is used to modulate the charge of the test mass. Then we have a second UV light injector that is being shined at a constant phase and just being used to compensate for the non-zero equilibrium potential and eliminate forces resulting from the coupling of the average test mass potential with its modulating component. So also shown here, you can see our signal being applied to these X electrodes here, this 12.3 millihertz signal. And this is the signal that we're applying to make our charge measurement. So essentially we have equal and opposite voltages being applied to our X electrodes. So that would be this 1 volt, 12.3 millihertz. So you can see 2 of our X electrodes here. And then on the opposite side, we have our other pair of X electrodes, which are receiving the equal and opposite potential for that charge measurement. And also in this picture, you can see these blue electrodes are our injection electrodes that are receiving that 100 kilohertz signal. So this plot here is showing our data from our experiment. You can see in the blue points here are our measured charge from the sensor. So we have test mass potential on the y-axis versus time. So this is our charge measurement at that 12.3 millihertz. And you can see that we are modulating the test mass potential at the 1 millihertz. And the bottom plot is just showing how we were linearly varying the phase of the UV light to produce this test mass charge modulation. All right, so after we successfully modulated the test mass potential, we were then able to demodulate the pendulum data to obtain the amplitude of the test mass charge, as well as the amplitude of the resulting force at our 1 megahertz modulation frequency. And from this, we were able to calculate our delta X, or the stray electric field in the sensor. So we repeated this modulation experiment for 5 different DC compensation potentials applied to the X electrodes. And each of these measurements was conducted for a duration of 10,000 seconds. So that's what this plot is showing on the right here. This is the measured delta X for each of those compensation potentials. And we also have our linear fit to the data. So we were able to use our zero compensation intercept here, so of our linear fit, to effectively find the delta X in the sensor. And this gave us a delta X of this 328.2 millivolts plus or minus 0.2 millivolts. And we also found that we got a test mass modulation, test mass potential modulation of around 133 to 136 millivolts for the compensation potentials we applied. And we also measured forces in the X direction on the test mass of up to 25 piconewtons with a precision of about 20 femtonewtons. Okay, so yeah, just to wrap up really quickly, this novel charge modulation technique, we've demonstrated that we can, this is an effective technique for measuring the stray electric field in a GRS with sufficient precision to compensate and suppress random test mass charging noise. And again, just some of the advantages of this technique are that the sensitivity of the measurement can be orders of magnitude better than DC methods if you choose your frequency in the sensitive band of the sensor. And in principle, you could measure the delta X on multiple test masses by choosing different modulation frequencies. It also offers some significant time savings over DC methods. And we actually have a paper that is coming out soon. It's under review at the moment, but that will be in Physical Review D. And that goes into much more detail about these experiments. I think that'll wrap it up for me. I'm happy to take any questions.
Thank you very much. Yes, indeed. Very interesting experiment and very nice talk. So, question for Stephen. Either in the chat or through YouTube, while you get rid of your shyness. Let me ask one question. So you found a native delta X on your test mass of 300 millivolt?
Yes.
Wow, that's big. It's a third of a volt. That's surprising. Do you know why? Is that what was like the treatment of your test mass surface? Or I mean, my experience is that we're talking tens of millivolts, not 100 millivolts. So, but maybe, maybe it's just random. But you have an idea why the number is so big?
I'm not quite sure. So the treatment of the test masses, I guess, would be similar to, I guess, what would be expected with Pathfinder. So we just have the surfaces of the sensor and the test masses are polished to a mirror-like finish and then gold coated. So similar treatment, I guess, to what would be expected with the sensor. So I'm not quite sure why that would be, I guess, larger than expected.
Never mind, it was just a curiosity. It may depend on so many things. So.
Right.
So other questions? People are shy today. Or maybe you are too clear. Well, I don't see any other. Well, then thank you very much. And thank you all the speakers this first half. And now, if I'm not mistaken, we have a break till 4:15. Is that right? Where is my support?
Yeah, that's correct. Yeah.
Okay, so let's reconvene at 4:15, maybe a minute before, and we'll go into the second half of the session. Thank you all. Enjoy your break. Are you there, Andrew?
Yeah.
So let's slowly get back to work.
Yeah, we can start in about 2 minutes.
Yes. Corey, are you there?
I'm here, yeah.
Great. Let's wait another minute or so and then. Sorry for missing to introduce you on my first go. Chairman always do mistakes, right?
Oh, you caught it immediately, so it was fine.
We have a very detailed instruction manual for chairman given from our Glasgow colleagues, but I wasn't able to follow literally.
You're doing a great job. Okay, Stefano, you can take it away.
Thank you very much. So welcome back to session 3 of LISA Instrumentation. And our next speaker is Corey Austin from NASA Goddard, who's going to talk about simulating micrometeoroid impacts on the primary mirror of the LISA telescope that I hope is not too severe. Corey, the floor is yours. And I give you a warning 3 minutes before your time.
Okay. Let's see. Are you all able to see that?
Yes, perfectly. Thank you.
My chart? Okay. Okay. Thank you, Stefano, for the introduction, and thank you all for taking the time to tune into my talk today. So, as Stefano mentioned, my name is Corey Austin. I'm a postdoc at NASA's Goddard Space Flight Center. And the subject of my talk today are the effects of micrometeoroid impacts with the primary mirror of the LISA telescope. Today's talk, essentially there are 2 main parts. We'll start with one slide for brief introduction and motivation, and then we get into the heart of it. The 2 main parts are simulating the micrometeoroid impacts and then evaluating the telescope performance based on the damage caused by those micrometeoroid impacts. So we'll spend a majority of our time on those 2 topics, and then at the end there will be one slide to wrap up with a brief conclusion. So to introduce and sort of motivate this topic, it was in the news around the 8th of June or so. The James Webb team released a couple of press releases that said that they had suffered their first noticeable micrometeoroid impacts just months into their flight. They had planned for this, so there were no impacts on the mission, but it was timely that these stories were coming out about Webb suffering from micrometeoroid impacts. LISA is planning to fly in a very similar orbit, so we'll see a similar space environment, and these micrometeoroid impacts could possibly affect LISA. So we wanted to take some look at that. Talking specifically about LISA, the current design of the LISA telescopes are such that there's no window or anything like that. So the primary mirror of the LISA telescopes are exposed to the space environment, which means that they are subject to micrometeoroid impacts. And the current design of these mirrors has them constructed from zero door, which is a glass-like material with a gold-like coating. And this zero door material is a sort of brittle material. So you would expect that with an impact with enough kinetic energy, you would see some of that substrate, removed, and a crater would be formed. So that's why we want to think about this with LISA. We also, as you're probably aware, each LISA spacecraft will have 2 telescopes, so there's a total of 6 telescopes. So this problem is something that's could multiply. We could see it across all the spacecraft. And then the 2 main parts of the talk are the micrometeoroid impact simulation. So we go through and we simulate micrometeoroids impacting the surface of the primary mirror, and then we calculate the damage that's done to it, and then we generate a surface map of the damaged mirror. And then we can take that surface map of the damaged mirror and use that to evaluate some of the telescope performance parameters, like the surface roughness of the mirror, the power throughput through the telescope, and the stray light that's caused by the craters. The first part of this is simulating micrometeoroid impacts, and in the next couple of slides, I'll go into each of these steps in a bit more detail, but I just wanted to give a quick overview of the process. So the first thing we do is to calculate the micrometeoroid flux that we expect through the region of space right outside the end of the telescope. And we do that to generate a population of micrometeoroids. We then assign a random position and velocity to each of those micrometeoroids and propagate it through the spacecraft towards the primary mirror. And then those micrometeoroid trajectories that intersect the primary mirror, we then calculate the dimensions, the diameter and the depth of the impact craters that are formed from that. So looking at each of these steps in a bit more detail, the micrometeoroid flux, the current version of the simulation I'm using, the micrometeoroid flux models that were developed by the team at NASA Goddard based on data taken from LISA Pathfinder. And there were a series of papers that were written in 2015, 17, and 19. And I've listed the most recent one there where these models are listed. But essentially, they use LISA Pathfinder to measure the momentum of micrometeoroid impacts. And then they were able to source out the sources of those various things and then come up with models for the flux of those. And so those are the models that I've used in this simulation. The flux is calculated over the momentum interval that's shown there. In a few slides, I'll show you why this number is important. Essentially, this momentum interval is important because you want to be sure to include enough micrometeoroid impact events to fully characterize the problem. But as you start to lower the lower bound on this, you greatly increase the number of events that you have to consider. But at some point, the damage to the mirror starts to sort of roll off. And so there was a balancing game here that was played with making sure that this interval considered enough micrometeoroid impacts to be useful, but it also needed to be able to run in time that was reasonable. So you'll see some of the tuning that kind of went into choosing where that number landed. The flux is calculated over a 10-year period, and then the resulting population is divided into 1-year chunks. This is done because the flux has a time and an area component, and if you only calculate over 1-year periods, then there's a chance that you miss out on some of the larger micrometeoroids. So the population is calculated for the entire 10-year period and then randomly divided into 1-year chunks and then applied as we want to look at it. If we want to look at a 4-year, a 5-year, 10-year mission duration, we can choose how many of the 1-year chunks we want to apply. Another choice that I made here was that the flux is calculated over an area that's slightly larger than the spacecraft opening. The reason for this is that the flux is calculated over that larger area, and then the micrometeoroids are assigned a random position and velocity within that area. And so that gives us a slightly different population of micrometeoroids each time we run the simulation. So once we've calculated the flux, the next part of it is propagation through the spacecraft. So right now the spacecraft is just modeled as a cylinder. You can see the dimensions of that cylinder right now, but that cylinder essentially represents the spacecraft, the thermal baffles that will be installed there. So what we do is we calculate the flux just outside the end of the opening of the spacecraft. And then we propagate those micrometeoroids through the cylinder towards the primary mirror. Any of the trajectories that are intersecting the spacecraft cylinder are being discarded right now. And then the remaining trajectories, they impact the primary mirror and they're saved and used for further calculations. In further iterations, I may think about trying to add something where micrometeoroids can bounce off of the barrel, but for now, for simplicity, I haven't done that. So those are just discarded, and we only use the ones that impact the mirror. So once we know which micrometeoroids impact the mirror, then we can model the crater that's going to be formed, the impact crater that's going to be formed from this. And I used a reference that's listed here. In this reference, there are several different models that are used that change various parameters in this crater size equation. I chose this core Pali model because it sort of gives us the most pessimistic picture, which we'll use in our analysis to determine whether we need to do further analysis or not. But we can use this equation to give us both the diameter and the depth of all of the craters that are formed. So we've created a population of micrometeoroids, we've propagated them through the spacecraft, determined which ones hit it, and then now we've determined how big the crater that each of those micrometeoroids is going to form. So we can take that information then and create a map of the surface map of the mirror. And in order to do this, we take each micrometeoroid impact and we apply it in series, and the depths are cumulative. So that means if two micrometeoroids were to happen to strike the mirror at the same point, the depths of their craters would add, and that was just a choice I made for simplicity. Once this surface map is generated, then we can get the first sort of metric from this, and that's the RMS surface roughness. And that's not necessarily a measure of telescope performance, but it is a number that has helped me in writing the simulation to kind of see how much damage is being generated on the mirror. And as you'll see in the next few slides, this is where I talk about the tuning that took place to find that correct or what seems to be the correct range for the momentum interval. So what you see here is basically the average, the RMS surface roughness of the primary mirror after, the given number of years on the x-axis there. And what I've highlighted here is that after 4 years, after a 4-year mission duration, with the momentum interval set at the default that I showed at the beginning, we would expect to see 1 microns of RMS damage to the mirror. The next step I took then was to increase that lower limit to the number that was basically the minimum momentum that was detected by LISA Pathfinder. And when you do that, you decrease the number of impact events, and thus you also decrease the amount of damage seen to the mirror. And you can see that we went from 1.7 microns down to 1 micron. So I wanted to go the other direction and see what happens if I lower that lower limit. So I lowered it by an order of magnitude from 5 times 10 to the minus 2 to 5 times 10 to the minus 3. And this changed the simulation runtime from the order of hours to the order of days. That's why there's only 4 years shown here, because this took about 4 days to run. And had I let it continue for the entire 10-year mission duration, this would have taken many more days. So I stopped it after 4 years just to see where we were. And you can see that with the increased number of events, we only see a small increase in the damage to the mirror. So this is something I used to tune it. It looks like, this lower limit that I chose, this 5 times 10 to the minus 2, is a reasonable number to use for now. In the future, if there's some reason we need to consider these smaller impacts, we can certainly change that. But for now, this is the sort of number that I've chosen. The next thing, the surface roughness is really just a metric I've used to look at how the simulation is working. It is something that we want to consider going forward. We want to think about things like how beam wander on a rough surface like that can affect the performance of the telescope, or if those craters on the telescope can affect things like wavefront error. But we haven't looked at those yet. It's on the list of things to do that you'll see at the end. One of the things that we think these micrometeoroids will affect are the power throughput of the telescope. So when these micrometeoroids impact the mirror, we expect that they will remove the highly reflective gold coating and also probably some of the substrate. The other effect of that is that some of that material could then be redeposited onto the secondary mirror. So there are 2 effects that could affect the power throughput of the telescope. And so what we did is we took a Zmax model and modeled the beam footprint on the primary and secondary mirrors. And then we just calculated basically the power lost by these micrometeoroid impacts. This next slide is just a detail of how I calculated the amount of—
3 minutes. 3 minutes to go. Sorry. Thank you.
Yep, I'll wrap it up. This is just the details of the calculation of how much of the ejecta gets deposited on the secondary mirror. The answer to that is not very little because the solid angle is small. This is a plot that shows the results of the power throughput results, and you can see that it follows pretty closely to the line that the power throughput loss is pretty equivalent to the damaged area. And from these initial results, it looks like the power throughput is not going to be a huge issue based on the micrometeoroid impacts. The thing I'm working on right now is the stray light effects of this. So each of these craters has the potential to backscatter light, and that's a concern. So I've just started putting this information into a Fred model to measure the light that's backscattered from these craters. Initial results show that not much light is backscattered, but I do want to do some more work on that. So that's to be continued. To wrap things up, we've developed a Monte Carlo tool that simulates damage to the primary mirror over the mission duration. And then we've used the results of that, which are a surface map, to start studying some of the effects on performance degradation of the telescope. There's still lots of things to do. One of the things that we haven't had a chance to do is to test this. There are some previous results on experiments where people have fired projectiles at similar materials, and I want to sort of reconcile that with what we've seen and decide, based on how those results come out, and also some of these other things like the stray light and then the effects of beam wonder, if it's something we want to think about setting up our own test of this to fire projectiles at gold-coated zero-dur and see how it works out. But those are all things that are to be determined in the future. So this is a work in progress, but I'm happy you attended the talk, and I welcome any questions or feedback.
Thank you very much, Corey. Very interesting, very nice talk. So question for Corey from the floor. So David, why don't you ask the question?
Okay, so thank you, Stefano. Thank you, Corey. It's a naive question. You sort of came up with the sort of surface roughness for the mirror after 1, 2, 3, or 4 years or whatever. First one is, roughly what sort of number of impacts are we talking about on the mirror surface per year or whatever?
Yeah, so per year, so yeah, this slide kind of shows it. With the number of impacts changes greatly based on that momentum range, and then some of the flux models, you can change that to a mass, and if you wanted to consider energy, but it doesn't really matter because it's velocity and a mass, or the two things you go into. Anyway, changing that momentum number greatly affects this. And so you can see here, this is the default range that I had selected, and we get 81 total impacts over a 10-year mission. And changing that momentum interval by an order of magnitude essentially changes that number by an order of magnitude. So when I went down to 10 to the minus 3, I saw on the order of 800 impacts. When I went up to the larger limit that Pathfinder saw, the number of impacts was in the single digits. So that number of impacts changes greatly depending on the momentum range. Yeah.
Okay, and if I'm allowed sorry, I was going to say, if I'm allowed a follow-up, since I probably didn't ask quite the right question, is how many of the impacts? How many of the impacts actually have an impact on the surface roughness? I'm presuming there's a size at which it doesn't really matter.
That's right. Yeah, and then the other part of that question is physically, what does it make sense in the model? Even the smallest micrometeoroid makes a crater, and physically that's not realistic. There is some physical limit where a crater is going to have not enough kinetic energy to damage the mirror. It's just going to bounce off. So there's that part of the question, but then also, yeah, like you said, and I think that goes into these sorts of plots, and that's what we showed here, is that once you go down below this momentum range, the impact craters are so small, their effect is it's somewhat outweighed by the larger craters, that I think that once you start getting into the tiny ones. They just don't matter.
Interesting.
Great, thanks.
Jennifer, do you want to ask your question or make your comment?
Sure. I made my comment. Thank you for the talk. The sort of preliminary conclusion I came to listening to you speak about the power throughput impact and the initial results from serialized modeling. It sounds like the micrometeor impact should not affect the performance of the interferometry, but then I thought to myself, maybe there's something I'm overlooking. So what is, I guess, your preliminary conclusion, and what are some other effects that you might look into with respect to the effect of micrometeoroids?
We can't hear you very well, but I think what Jennifer is saying, do you agree that this shows that micrometeoroid impact is not going to be a problem for LISA interferometry?
From the standpoint of, my understanding was she was asking about power throughput and sort of that ratio that goes between power throughput and backscattered light, because those are sort of two parts to the same equation. And yeah, based on this analysis, the preliminary analysis, it doesn't look like we're going to lose a lot of power on the transmit side. And then it doesn't look like we're going to generate a lot of backscattered power on the other side of that. So initially, no, it doesn't look like this is going to be a problem from that standpoint.
But let's study it carefully.
Precisely, yeah, exactly. Yeah.
And Harry Ward has a question for you. Harry.
Thank you. It's not particularly about it's about the damage, but from a different perspective. I remember from Pathfinder, people worried us enormously about the possibilities of surface damage to glassy materials being providing the opportunity for crack growth. And so you could actually have real structural damage from relatively small things. Is that something that we need to be concerned about, or are all of these impacts so completely trivially microscopic that we don't think they will impair the integrity of the bulk material?
Yeah, it's something that internally we've talked about a little bit, not so much along those lines, but more that, when we coat the mirror, there's going to be some tension, for lack of a better word. The coating is going to change the surface figure of the mirror. And as we impact the mirror, we may, forgive my hand wavy term, but release some of that tension and change the overall curvature of the mirror. That's one thing that we want to think about. Certainly cracking and things like that would be a concern. I think the next step for that kind of thing would be to take these surface maps and start to incorporate them with some of our mechanical models, where we can think about the surface stresses that are induced by the coatings and things like that, and what happens when you break that surface stress. That's something that we've only had some preliminary discussions about, but I think it is something that we will look at going forward.
Thank you.
Thank you. I think we should move on now. Thank you, Corey, again for this very interesting talk. And our next speaker is is UMINSKA from University of Florida, Gainesville, who's going to talk us about the dimensional stability verification, here we go, of the LISA telescope.
Thank you. Can you see my slides?
Yes, we can see, and I'll give you a warning 3 minutes before the end, right?
Okay, thank you. Good morning, good evening, and good afternoon, everyone. I am giving my presentation on behalf of NASA UF LISA telescope team. Here is the full list of the telescope team members from NASA Goddard Space Flight Center, University of Florida, and Texas A&M. Let me jump straight in. So the LISA telescope is an important part of a movable optical subassembly, or MOSA, and it enables light exchange between a spacecraft. So as a part of a scientific interferometer, it is required to maintain 1 picometer per root hertz length stability during the mission. The LISA telescopes are developed by NASA LISA telescope team as a Goddard Space Flight Center, and on Tuesday, Jeff Livas gave us a presentation about the telescope update. So if you missed that one, go and check it out. And the LISA telescope dimensional stability, or optical path length stability, testing will be carried out at the University of Florida, and that will be the main topic of my presentation. So probably you heard in our previous talks that for quite some time we've been preparing to test engineering development unit. However, due to some circumstances that I will talk about later, we decided to measure a structural thermal model instead and use our experience with the EDU testing preparations, which will allow us to test the structural thermal model before adoption review and get some preliminary results. So a little bit of a historical background. Our original plan consists of a rigid test bed or telescope test structure that will host the telescope and form optical cavity around it. So this optical cavity around the telescope, together with some ultra-stable reference cavity, will be placed in the vacuum tanks, where the two 1064 nanometers lasers will be locked to their individual cavities, and a differential frequency between those lasers will correspond to the noise length of the telescope and our TTS, telescope test structure. That's why we also require that our telescope test structure will meet the requirements such that excessive noise could be allocated to the telescope. So during preparations for our measurements, we did some simulations of tilt to length coupling, and we discovered that there is the tilt to length coupling coefficient that is proportional to the off-axis interface of the telescope. This was mentioned in Ewan and Jeff presentations on Tuesday. I'll just quickly remind that due to the fact that we have off-axis interface here shown on a picture, we have this coefficient that is proportional to this to the distance between on-axis beam and off-axis interface. So this will be not only a problem in our measurement, but it's also sensitive to optical bench and telescope relative alignment. And a proposed solution was to redesign the interface and fold the beam back on a primary mirror of the telescope on axis. This was discussed in Jeff's presentation on Tuesday as well. So this solution was accepted 3 months later. However, it was too late to change the NASA EDU design, and as the project was pretty advanced. But the only thing, not the only, it highly impacts our measurement. So we had a few ideas how to mitigate this problem. First was to rest EDU on our telescope test structure, but due to the fact that that could potentially affect the alignment of the telescope, we scrapped that idea and we introduced the periscope that will bring the beam in the same way as the proposed redesign back on axis. Not really in the same way, but that will be additionally attached to the telescope only for our measurement. So here I show the optical schematic, how it looks, and in the middle is this proposed periscope. And there are a few requirements on this periscope. First is that it has to stay aligned within itself to picoradian level. Second, it has to stay rigid with the telescope. And three, that it cannot be mounted permanently to the telescope to enable further measurements, for example, wavefront sensing at the Goddard. So we came up with the idea how to mount it, which is shown here on the top right graph, that we have soft spring that is threaded here through the periscope, and this metal clamp grabs the primary mirror from the back. So this, as you can see, adds quite a lot of complexity to a already challenging experiment. Two, we also learned that building such a periscope is not easy. And three, we still have quite a stringent requirement on our alignment of the TTS to the telescope, which is micrometer and microradian static alignment, and nanometer and nanoradian in-band jitter during our measurement. So in addition to that, we got hit by a schedule impact. So the engineering development unit will be delivered to Goddard Space Flight Center for wavefront testing in May 2023, where the structural thermal model will be available in December 2022, so this year. So we decided to, basically a few months ago in April, we decided to use our prior experience with the EDU preparations and test the structural thermal model. The one big difference is that the structural thermal model, as being a complete mechanical model of a telescope, doesn't have an optic that is coated or polished. So we have to make a little bit different approach to this measurement. And now, how are we going to do that? So we still wanted to introduce optical cavities to the model. Here on the left is our UF STM mockup. This is primarily used in, we use it for fitting of mechanical components, testing alignment. However, we do all of the design studies on the actual STM model. We also show this one due to NDA here. So as I mentioned, we want to introduce optical cavities to the STM, and there are a few requirements on that. One, that those cavities have to include the total optical path length of all of the mechanical interfaces and bonds. Two, the mounting mechanism of those optics cannot add noise to the measurement. And the advantage of using STM is the flexibility to design high finesse and low loss cavities that will be less susceptible to technical noises in our sensing system. We also have certain flexibility to position those mirrors and tweak a little bit those cavities. There is no need for any periscope, and there's no stringent requirement on the alignment. And in addition, STM will be available 5 to 6 months earlier, which gave us a chance to get the preliminary stability results for adoption review. And lessons learned from an EDU, how we actually want to attach those mirrors to the STM. So let me a little bit describe our telescope test structure, which is shown here in the middle. It's built out of ultra-low expansion glass plates that are bolted together using the steel dowel nuts and screw mechanism that is shown here at the top. And the cavity mirrors are pressed against these plates using the soft spring washers, which are held by the retaining ring. And the only part that is here epoxied is this metal ring that supports the mirror. And this epoxy is decoupled from the optical path length thanks to those soft springs. So the length of the structure is defined by the low expansion side plates. And we prove the stability of the structure using a scaled down prototype, which is shown here on the left at the picture, which is P, as we call it, PTTS. And its length stability curve is shown on the right. The red corresponds to its length stability, which meets the requirements in all of the frequencies. The red, the black dashed curve is the LISA requirement, and the blue curve is the length stability of two reference cavities measured against each other. We also measured the CT equivalent of 33 ppb per Kelvin for the structure, which is less than we allocated for the false structure. So now let me talk about the cavity design within the STM. So as I mentioned, we wanted to include all of the critical bonds. So we introduced two optical cavities. One is between telescope primary mirror and a secondary mirror, and that includes the interfaces between the telescope tower and M1, as well as the gasset bonds. Cavity 2 is between M3 and M4 assembly. So altogether, they include all of the interfaces. And now let me just look closer on each of those cavities and discuss how they're mounted. So we have the cavity mirror 1 mounted on M1. This gray piece corresponds to, represents the curvature of STM. So our mirror is a wedged zero-door square that is shown here by this purple square. This center mirror is only for the purposes of alignment and some tests, which I will show in a second. So we press this wedge zero-door mirror using the peak mask that holds this mirror. And this is pressed with the steel springs that are shown here, which are held by this metal frame that is epoxy 2 and 1. So the only epoxy is on this frame, such that, again, it decouples the bonding from our optical path length. And
Ada,
to position this...
Ada, sorry to interrupt you, 3 minutes.
Okay, thank you. So this frame will be positioned on M1 surface using this rather complicated looking metal bar. This is just for the alignment purposes, so we can bond this frame, and later it will be taken off for the measurements. Our second mirror of the cavity will be mounted in exactly the same as used for our TTS. It will use some intermediate zero-door piece that will contact the M2 from the back, and again will be pressed against the back of M2 using the soft spring shown here. So this is a cavity 1 and the cavity 2. It looks a little bit, there's a lot going on in this figure, but the top middle one shows the side view of this optical cavity, where we have 2 end mirrors attached to the telescope tower. And then again, those are the zero-door intermediate pieces that are pressed against the tower using a spring. And we use a standard zero-door optic that is again pressed against this intermediate pieces with a spring washer. And here M3 and M4 again are not polished or coated, so we have to introduce our own optic. In the same way, we use a peak mask and springs that hold these mirrors in place. And here is also the sort of side view how this cavity looks like. In addition, we use the highly reflective optic to reduce any cavity losses, and as I mentioned before, maintain a high finesse and less susceptible to the noises cavities. And here I'm just showing a few pictures from our lab. Those are as fresh as from yesterday. Joe Gleason sent me some updates. So here is our aluminium mock-up that we use for the mechanical feed testing and alignment testing. Here is the zoom into M2 mock-up. I can see the M1 curvature mock-up. Here we have M3 and M4 assembly on the back with the mask and mirrors for the alignment test. Here is also show the first spring that was attached to this to the back of M3 and 4 assembly, and the springs being manufactured at our UF machine shop. On the left, I am also showing pictures of our vacuum tanks with the vacuum tank with the cooling jackets, which is getting ready for the STM testing.
You should really wrap up, Ada.
Yeah. And to conclude, for the STM testing, we are getting ready to receive STM at UF in December 2022. We are preparing for stability testing for the adoption review, and we're looking forward having preliminary results in the room temperature. We will continue testing the various temperatures and ranging from 10 to 25 C. And for EDU testing, we have good understanding on how to run the stability test with EDU, and if it's necessary, it will be tested at UF in a later time. Thank you for your attention, and happy to take any questions.
Thank you very much, Ada. Very nice talk and very challenging and interesting work. So, Alexander, you have a question. Why don't you ask? Alexander? Oops, no voice. Okay, so Alexander is asking, you mentioned most readouts are cavities. Is the length readout then via PDH? Don't ask me what it means. You understand?
Pandas driven hole. Yes, this is via PDH locking.
Okay, thank you. Any other question for Ada?
Stefano, can I ask one?
Sure.
I would just be interested to know how you were getting stable injection of light into the cavities, because that can often be the limit to how well your cavity will perform. But I didn't see any sign of that in your presentation.
Actually, so we have, for our prototype, we had this EDU prototype. We had, sorry, the TTS prototype. We had just all the components through the vacuum was fiber feature, and then we had all of the components on the same bench, and we didn't see any actual problem with the stability of the injection. So I believe any pointing will mostly show up as a contrast in the error signal PDH locking, but it doesn't introduce a significant amount of noise in our cavities.
Thank you.
Okay, thanks. Jennifer, you have a question. Would you mind to ask?
Sure, hopefully you can hear me better. How do you control the tolerances when you're mounting the mirrors on this tune?
Could you hear? How do you control the tolerances when you're mounting the mirrors to the STM?
Mechanical tolerances. I'm not sure. Sorry, I'm not sure if I understand the question. So we have those frames that are actually clamping here at the back, and we will have to align this mirror that is within, maybe here it will be better to see, within this frame, and we are planning to use some shims, and we also have those holes for the micrometer screws for some precision alignment. But once it is aligned, it will be retracted and it will be held by the spring mechanism.
Mm-hmm. Thank you. Any other question? I see a comment by Paul Fulda to Harry. If you're interested, look at the chat. Any other question for Ada? If not, thank you, Ada, very much for this very interesting talk. And last but not least, we move to the last talk of the day, which is Lorenzo Sala from the University of Trento, who's going to tell you about all you wanted to know about glitches in LISA Pathfinder. Lorenzo, that's your floor is yours, and I warn you at 3 minutes to the end, okay?
That's fine. Thanks. So thank you for the introduction. And as already said, I'm Lorenzo Sala, and I'm about to talk about the transient acceleration glitches detected in the LISA Pathfinder mission. So I'm going to talk about the detection and the detected properties, some correlations with some other telemetries on board the mission, and something about the possible physical origin of these events. And if you're interested in some more detail, you can find everything in our recently published paper that is on the archive. I put the reference here. And so I'll go fast on this slide since some speakers have already talked about the LISA Pathfinder mission. And we are talking about the differential acceleration between two test masses that were identical to what will be used for LISA. And the main measurement of the main objective of the LISA Pathfinder was actually measuring the quality of the free fall of these test masses along a sensitive axis that was in which there was a measurement by a very sensitive interferometer that is depicted here. And so the first test mass was actually freely falling in space, and the spacecraft was following it to keep itself centered about it. and the second test mass was instead actuated with some electrostatic forces which were applied to keep the second test mass centered with respect to the first one. And everything was measured by the interferometer, and the actuation was performed by the so-called gravitational reference sensor that also provided a capacitive sensor, a capacitive readout of the position of the second test mass, and of course of the first and second test mass. Sorry. And after some days of commissioning before starting the operation, LISA Pathfinder began its ordinary operations with these ordinary runs, which were performed at 22 Celsius and also 11 Celsius. We call all of them the ordinary runs. And what I would like to notice is that there was here a period of 12 days in which the temperature was brought down even further to about 2 Celsius. And this period was really important for the glitch properties, as you will see. And after that period, the temperature was brought up again to 22 Celsius. So here we have these 12 days of cold runs and these 138 days of the ordinary runs. And so what are we talking about? We are talking about these glitches in the differential acceleration between the two test masses. And we detected two families of glitches, one that we call the impulse carrying glitches. That were detected all over the mission, and where many of them were very long lasting. And the second category of glitches that we call the low impulse glitches that were very fast and were almost detected, let's say, only during the cold runs. The name of the glitches is very easy to guess. Actually, the second family of glitches didn't have any measurable impulse. That is, the glitches didn't transfer any net velocity to the test masses. Whereas the long-lasting and impulse-carrying glitches actually had an impulse, and the impulse is nothing else than the integral below the curve. The glitches in this family could be modeled and fitted with a nice exponential decaying models. And each glitch is associated to two parameters. The first parameter is the net transfer velocity to the test mass, and the second parameter is an effective duration. So we can show some plots with the correlation between this impulse and the delta, the duration. You can look at the top left plot that shows the ordinary runs, the glitches in the ordinary runs and positive glitches. And you can see that the duration is spanning from seconds, tens of seconds to hours. And the transferred impulse is spanning from a fraction of picometers per second to even nanometers per second. So on a large, spanning many orders of magnitude. And you can also see that during the cold runs, the distribution was somehow different. For example, we didn't detect many of the long-lasting glitches. And what you can also see is that during the cold runs that I recall was 12 days, we detected many more glitches than during the 138 days of the ordinary runs. What we can also see about the impulse carrying glitches is that these events showed up with a Poisson distribution, with a rate of about 1 glitch per day, and this rate was almost stable over the whole duration of the mission. What is remarkable is that this rate of one glitch per day went back to 1 glitch per day even after the cold runs. So here the question is, what happened during the cold runs? Well, during the cold runs, the situation was really different. You can see that the rate went from 1 glitch per day to, let's say, 20, 40 glitches per day. We are zooming in these 12 days. And you can also see that the rate was not as stable as it was during the ordinary runs. Indeed, the temperature in these runs was not as stable as it was in the ordinary runs. For example, we can see here a fair dependence of the rate on the temperature. The rate is going down while the temperature is going up, and it was back to normal after these cold runs. Here we tried to answer a question about the nature of the glitches. So the question was, are these glitches real forces, or are they just features in the interferometer readout? Well, we had the interferometer measuring the distance of the test masses, but we also had the capacitive sensors. So we could use both. For example, here in the black line is the response to a glitch from the as measured by the interferometer. The orange line is the same measurement by the capacitive sensors. And the green line is what we would measure if the glitches were not actually true forces, but just features in the interferometer. So we can, from this, we can say that these glitches were actually real forces acting on the test masses. And given that the glitches are real forces, then why don't they have any associated torque? Well, we analyzed also the angular acceleration time series, and we can say that only 4 out of the 400 and something glitches had real torque associated to them. So we are real torque, let's say a torque that is not compatible with 0. And so we can use this figure, for example, to say something about the origin as electrostatic forces, because a lever arm of 11 millimeter would be a pretty strong signature of glitches being due to the electrostatic actuation. And so it is important that these glitches have actually no torque, let's say, unless of these 4 glitches. So we can now go to the discussion part. And first of all, I would like to talk about the two-sided glitches, which I didn't talk that much about previously. I just focused on the first family. And we actually detected some significant coincidences between the two-sided glitches and some other interferometer channels that were present on board the mission. And so we can say that these glitches are very likely due to interferometer anomalies. And I would also like to stress again that these glitches were measured most of the times only during the cold runs and not during the ordinary runs. Only 4 glitches were measured. Only 4 low impulse glitches were measured during the 140 days of the ordinary runs. And what remains is the discussion about the impulse carrying glitches, for which we don't really have a smoking gun, but we have analyzed many time series, and we have excluded many effects. For example, we have analyzed the possibility of glitches being due to gravitational signals, such as permanent displacement of structural components or parts in the spacecraft. We have analyzed the possibility of glitch being due to platform acceleration in common modes, such as, for example, micrometeoroids, that we have to exclude, for example, for many reasons, but for example, about the permanent displacements, because the permanent displacement would also give a permanent force to the test masses, and we detected no permanent force, so that is to be excluded. We also analyzed the temperatures, temperature and time series of temperature sensors positioned in close proximity to the test masses. We also have analyzed the magnetic field time series without detecting any triggers in this time series. And we can also say that we had enough resolution in those time series to exclude many effects, to exclude the possibility of detecting. We had enough resolution to see glitches in those time series resembling the glitches in the delta G time series, giving enough force to be detected, of course. So we had to exclude the magnetic forces and the temperature time series. And so we're left with the electrostatic forces. As I already said, we didn't detect any stable lever arm of these glitches. So this is our first thing that could exclude the electrostatic forces, even though we cannot exclude them at all, but it's really unlikely, also because it's really hard to think at mechanisms giving such long-lasting glitches with the electrostatic forces. And so another thing that I'd like to stress is that
Lorenzo, 3 minutes.
Thank you. This kind of transients were not detected in the pre-flight tests, so it's kind of unlikely that this was the reason. So we analyzed one last thing, that is the outgassing environment, the outgassing bursts, let's say. Even though we don't have a definitive smoking gun that this was the phenomenon, but what we analyzed with some molecular simulations is the possibility of that these glitches were due to gas, possibly water, that was released from let's say pockets or pores in the structure. And actually, the molecules, before leaving the vacuum chamber and being vented to space, the molecules could hit the test mass and transfer a net momentum to the test mass, actually transfer giving a differential pressure between the opposing phases. And what is remarkable is that just a fraction of nanograms of water would be enough to explain the observed picometers per second typical glitch. What is a bit harder to explain would be the time profile, but if you're interested in more details, you can find them on the paper, of course. And another thing of this model is that this could possibly explain the sudden rate increase during the cold runs, because the gas could be released by this by mechanical deformation or by mechanical stressing. Mechanical stress is being released, and so it could possibly explain the sudden rate increase. And so here I'm concluding. I'm concluding with the things that I just said. And what I would like to highlight is that about LISA. There are some people in some groups of the LISA consortium that are now studying the possible impact of the LISA Pathfinder-like glitches on LISA if glitches showed up as they did on LISA Pathfinder. And thank you for your attention.
Thank you, Lorenzo. Thank you for this nice talk. So, question for Lorenzo. I can't ask a question. I'm a co-holder.
If I could come in, David Robertson here, ask a couple of questions or related ones.
Yes, go ahead.
So you're seeing the glitches along the sort of plus and minus x-axis. Can you tell essentially which test mass they're in and which way they're pushing? And a related question is, you're looking along the plus minus x-axis. I presume the answer to this next question is there isn't the sensitivity, but can you see it in other axes as well?
Yes, so I could show, for example, this plot. I actually didn't talk about the dashed line. The dashed line is the detection threshold of these glitches at this SNR equal 3. And so we could measure, we could not detect any glitches below this detection threshold curve, of course. And yes, along other axes, the sensitivity of the along other axes, of course, we don't have the interferometric readout, so we have to rely on the capacitive GRS sensor. And yes, the sensitivity along the other axis is much reduced, and so we could not detect glitches with this sensitivity. And so, for example, if this curve goes up, it excludes completely these kind of glitches. So we could not detect long-lasting glitches like this in the Y and Z axis. Yeah.
Okay, and is it a true statement that because you're looking at the differential acceleration, you can't say which test mass the glitches are happening in?
Yes. Yes, indeed.
Yes, exactly. Yes.
Well, thank you very much. Really enjoyed that talk.
Thank you.
Alexander, you want to make your comment? No, it's a comment that says that your talk is much better than the paper. Well, is that a compliment? I don't know. Thank you, Alexander, for your comment. Any other question for Lorenzo? I don't see any. Then I think we can thank Lorenzo again. We can thank all the speakers for this very nice talk. I really enjoyed them, all of them. And I think we close the session and we have a very long break, right? Am I right? And we start again. Andrew, may you support me here? We start again at 20 European time for the long session, for the plenary session, right?
Yeah, it's 8 o'clock plenary session.
Okay. Thank you very much, everybody, for joining us, and enjoy your long break.
Thank you.